Okay, and the last section of problems that we added were our trig identity problems. There's going to be those 5. The first 3, we just need to simplify down as small as possible. But 54 and 55, they have the equal sign, so we know that we have to turn the left-hand side into the right-hand side, so we don't touch the right-hand side. When we did trig identities, we kind of had these 4 rules that we kind of ran down the list. Okay, every time we had a problem. The first thing is, does something factor in our problem? And that can be as small as a GCF. That could be difference of squares. It could be just any type of factoring. But something, if it looks really gross, like if we have, you notice there's a common term or you have bigger exponents you want to factor. Okay. Another thing we looked, if we had more than one fraction, do I have to get common denominators to combine a lot of stuff into one big term? Number 3, the Pythagorean identities. Those are the ones, okay, they have the squares, okay, and the ones in them. When we look at that, they have like sine squared plus cosine squared equals 1, 1 plus tangent squared equals secant squared, and then, and then there's one with cotangent squared and cosecant squared. So those are the things we look at. If you notice that there's some bigger exponents and you maybe have a 1 somewhere in there, that we could look at those. But the last one, if all else fails, or if your problem starts pretty simple, then we would look for sines and cosines. If we have we just switch everything to sines and cosines, because there's so many identities that we have that involve sines and cosines, and every trig function we can write as something with a sine or a cosine. So when I say simple identities, things that don't look too complicated, like 51 and 52, they don't look very complicated. We just have to get this as small as possible, and so these would be ones where maybe sine and cosine, we can just start out there. If I run down the list, they don't have common factors. They don't even have squares for me to do Pythagorean identities or to factor anything. There's one of them that has a fraction, but it's already one fraction, so I'm really kind of down to my last option of sines and cosines. And 51, this is great because you already have a sine of x, so really I just have to change secant into something with a sine or a cosine. And if we check the back of our identities, we know that secant is 1 over cosine. It's a reciprocal identity, so we can switch it there. And now we can combine this into one term that says, well, this is just sine of x over cosine of x. And we know that sine of x over cosine of x is really tangent of x. And now we've simplified it down as small as we possibly can. Okay? So we know that you could have more than one term, but most of the time you're just going to have one term when you simplify it down to. Okay? We can do the same thing with 52. I have this fraction that says cosecant of x over secant of x. Well, there's really, right now, nothing we can do. There's no factoring, there's no fractions to combine, there's no Pythagorean identities with squares or ones. So again, I'm back to this rule of maybe I just need to change it to some sines and some cosines. Okay, so we're going to check the back. I'd have to change both of these, but I do know that cosecant is 1 over sine of x. Okay, so I could do that. Now we have one big, gigantic tower of math. And secant, as we just talked about, is 1 over cosine of x. And so this looks really ugly, but it's going to be helpful in about 2 seconds. Okay? Instead of dividing by a fraction, we know that dividing by fractions is the same thing as multiplying by reciprocals. So let's do that instead. Okay? So it's really 1 over sine of x times cosine of x. And a lot of the times we like dividing by reciprocals because, we're like, oh, maybe something will cross out, it's going to divide out. I don't see anything that's going to divide out because cosine doesn't cross off with a sine. So we're just going to combine this into cosine of x over sine of x. But this is actually helpful because we just talked about sine over cosine was tangent. But I have cosine over sine, which is going to be cotangent. Okay? It's a reciprocal of each other. So cosine over sine equals cotangent. Again, I get it shrunk down to as small as we possibly can. Those are some things we're going for. Sines and cosines are really, really, really helpful. When we get to 53, 54, and 55, now we start seeing bigger exponents. So this is where possibly factoring could come in, or at least Pythagorean identities. And on 53, I kind of see some relations with the top and the bottom. Okay, we know 9s and 3s sometimes go together. I see some squares. But what I do not want you to do is say, oh, well, there's a sign here and a sign here, and then there's this will cross off. No, you can't do that. Okay, we know in math, for me to say there's a 3 here and a 3 here that I can divide out, this has to have a 3 and this has to have a 3. And they don't. I can't just cross it off of a piece on the top and a piece on the bottom. Okay, I have to be able to cross it out of everything. Okay, but I think maybe I can get the bottom to look similar to this, or sorry, the numerator to look similar to the denominator if I can factor the top. And I can factor the top because if we notice, sine squared and 9 are both perfect squares. So what I have to do is say, okay, well, I could factor the top part into 2 pieces. Difference of perfect squares, you always can. Okay? So the sine is first, right? Sine squared. So in order for me to get a sine squared, I'd have to have a sine in the front of both of these factors. Okay? And the 9 comes second. And in order for me to get this 9 that's back here, when I multiply them together, perfect squares, I'd have to have a 3 and a 3. Okay? But when we know that if I FOIL these 2 pieces together, I have to get back to this. Okay, if I multiply them together, I have to get all the way back to sine squared of x minus 9. And there's no middle term. And for me to not have a middle term on difference of squares, I have to have a plus and a minus. Okay, so they look almost exactly the same, except you have a sine of x plus 3 and a sine of x minus 3. So my denominator stayed the same, sine of x minus 3. Okay, but now I have something on top and bottom that is similar. I have a sine of x minus 3 over a sine of x minus 3. That can go away, and I can be left with sine of x plus 3. It's as simplified as it can be. It's as small as possible. It happens just to be 2 terms. That's okay. It could be more than 1. But it's as small and simplified as we can get it. Okay. So on 51, 52, and 53, we shrink it down as much as we can. On 54, okay, and 55, it's a little bit different because I know what the answer is. Surprise, the answer is going to be cosine. I just have to figure out how to do that. Okay? And so we run down our list. Do I factor? Well, it kind of looks like they already took a GCF out, right? It's kind of hanging out on the outside. And so when we get something that looks like that it looks like they already did a GCF, we kind of want to fix the piece that's left over. I'd like to see, excuse me, if I could change maybe this 1 minus sine squared into just one term. Okay, I don't want to break it apart. I don't want to make it lots of different terms. I'd like to make it just one piece. And so it's not really a fraction I can combine, but it does have some squares and some ones. So I'd like to see maybe if I could do a Pythagorean identity. Okay, and so we would jump to our page to check out all the identities that had a 1 and a sine squared in it. And we would see this identity right here. It's a sine squared plus cosine squared equals 1. I know there's supposed to be x's in there, but we all know they're supposed to be there. Just go with it. Okay, so I don't have this identity exactly in my problem, but I want to see if I can actually move these pieces around over here, either side, to see if I could do that. If I could actually get the 1 minus sine squared to show up over here. Okay, well, the 1's on this side. If I needed to say minus sine squared, then I'm going to minus the sine squared from both sides. Okay, cosine squared is going to stay put, and I get 1 minus sine squared, which is now what I want. This and this match. Okay, so now I can swap out and say, well, instead of putting 1 minus sine squared, I'm going to put what 1 minus sine squared equals. And 1 minus sine squared really equals cosine squared. Okay. Right? 1 minus sine squared equals cosine squared. Let's swap it out. All right, so we did help ourselves, right? We took 2 terms and got it down to 1. Let's try to get smaller. I just need 1 cosine. I have a secant and a cosine squared. Okay? So when we get here, we've shrunk it down even farther. Well, we have a lot of sines and a lot of cosines, and we want to get an answer that's in cosine. Let's see if we could maybe rewrite this little piece, this secant, as something with a sine or a cosine. Preferably cosine, so I can make them all match. And we can. Okay, we know we've done this at least twice so far, that secant is 1 over cosine of x, but I'm multiplying that by cosine squared of x. Okay, and if we see what we can cross off, I have 1 cosine on bottom, but I have 2 of them on top, so it's kind of like crossing off the exponent. And ta-da! I get cosine of x equals cosine of x. It really does. It's kind of like a proof. You got to show me that the left-hand side really does equal the right-hand side by using all the pieces that we know. Maybe we got to swap something out using Pythagorean identity. Maybe we have to change things to sines and cosines. But we can use all of our tools. All right, and 55, the last question on your review looks really gross. It's actually probably one of the cooler, easier problems that we've done. Okay, we're going to start going down our list of rules. Okay, we know what the answer needs to be, so we just have to make the left-hand side look like that. So let's start at the top. We got to talk about, could we factor anything? Well, it's not looking like difference of perfect squares, but the very first question we always need to ask ourselves is, out of the terms that we have, is there a common factor? And the answer is yes. Both of these terms have a cotangent in that we can factor out as a GCF. So we kind of write it on the outside. Okay, we're going to write that cotangent out here. So I'm left with sine squared of x plus cosine squared of x. Okay, and then we got the right-hand side. So now it kind of looks like number 54. 54 started with it looked like they had already GCF'd something out, but now we did that. Okay, so again, once we have a piece on the outside, let's see if we can just fix what's left over. Well, hopefully, this little piece on the inside kind of sets off alarms in our head that we know something about sine squared plus cosine squared. And there's a big fat identity on our unit circle page that says sine squared plus cosine squared is really just 1. Okay, so I can replace everything in that chunk with just a 1. Now I get cotangent times 1 equals, cotangent. Looky there. And in 2 steps, we go from something that looks pretty awful to something that looks pretty nice, and we get our answer. Okay, remember that just because these look gross doesn't mean they are gross and super hard. We just need to keep our rules. Okay, factoring, fractions, Pythagorean identities, and sines and cosines. Maybe jot it down somewhere, okay, on your review. Kind of keep making note of it so we can study that for our final. You guys will do great, I promise.